Okay, guys, so I would like to spend a couple of slides only on UVVs and IR, because again, we already discussed the UVVs is not it doesn't really give you too much information for the task that you're gonna, for the exercise you're gonna solve at the workshop and at the exam. So basically just remember, whenever you see UVVs in your set of spectra, just remember to see if there is an absorption, especially if it's a strong absorption. You can probably guess there is either aromatic system, most likely, or a very highly conjugated system, which sometimes because aromatic system is a highly conjugated system, so it absorbs a lot the UV. Okay, so there are all these tables for UV, but honestly, for the economy of your exam, UV doesn't really matter. Only check if there is an absorption or there is not. So you know there is a conjugated system. Most likely there is an aromatic. So if you see something like that, and there is an absorption, or sometimes, depending on the exercise, I just say on the UV you notice that there is absorption. It may be that it comes from conjugated systems, okay? There is no much more you want to say on the UV. There is no much more you need to report to the UV, okay? FTIR. I don't want to stay too long on FTIR too, because you used FTIR to find your whole degree for the moment, so you know where the most recurrent peaks are. This is a table, by all means not comprehensive, so feel free to, when you revise and we do this kind of exercise, feel free to get tables from other books, from the internet, from wherever, but normally what the FTIR says is if there is a particular functional group or not. It doesn't tell you too much where this functional group is, what is connected to, or any other information that normally you can get from especially proton and carbon. Well, a little bit of mass spec too, but especially proton and carbon, okay? So FTIR, revision for FTIR for the workshop or for the exam, just remember the main bands, the main stretchings and bendings of the IR. So for instance, you should always see if there are aliphatics, normally it's around 3000. If there is, FTIR is really important whenever you see carbonyl peaks. Carbonyl bands are very strong, very intense. You can guess from FTIR if that carbonyl belongs to an ester, a ketone, but in order to do that, I will probably go back to the carbon 13 because it gives you more information. So you confirm, so for instance, you see FTIR, you see maybe a big band of carbonyl. You mentioned your report, I see that around 1700, 1600 something, there is a strong band which suggests the presence of a carbonyl peak, which might be or not be confirmed by the carbon 13, for instance. Then you can say 3000, maybe there is aliphatics. Be very careful with the bands between 3500 and 3000, because this is where you look for alcohols or amino groups. If there is an amino group, depending on the kind of amines you have 2, 3, 1 bands. So be careful, because that number of bands and the shape of the band on the IR, it's also a good hint that it is maybe a substituted amino group instead of a free amino group. So be careful with those. Then 1600, more or less between 1600 and 1500, you can confirm the presence of aromatics, because 1600 more or less is where you start seeing double bonds conjugated. So have a look. If you have aromatics, let's say you see UV, there is an absorption, you go to the IR, there are several intense bonds at between 1600 and 1500, you can confirm, you can use these numbers to confirm that there is a potential aromatic group. Remember that both for FTIR and for both FTIR and mass specs give you a lot of peaks. For the common method of the exam, try to comment and to work out, if you have to do any calculations, try to comment and report only the peaks where I put numbers. So if I highlight a peak, something like, okay, I highlight the peak on 3,200 something, and you have in the formula nitrogen, there might be an amino group. So you want to comment that, you want to report that, because eventually what you're going to create, we will see with exercise that they will come more out, probably will become easier. But what you want to do is eventually reporting, starting from the degree of unsaturation. The calculation of the degree of saturation has this, I expect this in number of unsaturations. Then you go in a sequence, something like from the FTIR, I say 3 main bands. These belong to this belong to that, blah, blah, blah. Mass spec, there are some couple of those that we call magic numbers, the one that are recurrent, the one that if they are there, they're actually telling you that there is a specific group. So again, on the mass spec, you can see, I can see this number, let's say I can see 43. It's an acetyl peak. But I don't know anything else about the rest of the molecule. But for the moment, you take the acetyl peak on one side, and that might help. Maybe with the mass spec, the rest of the peaks that you're going, apart from, of course, if you see the molecular ion peak, but maybe in the mass spec, if you want to say something really meaningful, you will wait until you interpret proton and carbon. Once you have an idea of the structure, or at least part of the structure from proton and carbon, maybe you go back to the mass spec and look for maybe this fragmentation. If I'm right, this fragmentation might come from loss of this group. Okay, so you don't just analyze one spectrum per spectrum. You always go back to the same, let's say, mass spec, or you go back to FTIR. Let's say that after you interpret the NMR, you say, yeah, but I should have, I don't know, maybe this is not a carbonyl, maybe this is nitrogen, but it's not an amino, maybe it's a nitro group. You go back to the IR and see if there is the potential presence of a nitro group instead of the amino group. Or maybe the opposite. You discard some information, something like, it looks from the structure of the proton, the structure that I try to work out from the proton NMR, it looks like I may have an amino group, but I don't see it by IR, so it cannot be. And if there is not amino group by IR, it's not there. Full stop. So don't try to do so. I've seen so many people trying to work out carbonyls where clearly there was not a carbonyl. If you don't see the carbonyl on FTIR, if you don't see the carbonyl on carbon 13, don't make up your structure so that you eventually end up with a carbonyl, because that is not a carbonyl. We will see with examples. Remember the main stretchings, higher frequencies on IR is the stretching, lower frequencies are normally bendings, vibrations. Again, use the tables, try to remember some of the numbers because it's really helpful. Some of the most recurrent numbers, but there are 4 or 5 groups, 4 or 5 bands that you want to remember from FTIR, no more than that. So when we say you need to remember some of the numbers, we're not talking about list of numbers. I'm not talking about this table. You don't need to remember this table as it all. Some of the most important peaks, because even if you just see, and if you can just comment the peaks that are highlighted and put the numbers on, I am pretty sure that is more than enough. It means that is more than enough for you guys to know. I don't expect that. There are no trick questions. I don't expect that you remember exactly that number and only that number tells you something. Be careful with the IR. Sometimes, if you have, especially once you calculate the degree of unsaturation, be careful because triple bonds, something like nitrile groups or alkynes exist. Sometimes people discard and something like, no, I need to find something. IR tells you about nitrile groups are quite small, but they are in a very isolated position of the spectrum. Normally, both alkynes and nitriles are about 2,100, 2,200. There is not much more, which is very meaningful for you to look at. So if you see a peak in that region, it might be actually very meaningful, very significant, okay? If you go below 1,000, around 1,000, 1,100, I mean, 1,100, something like that, you can say maybe this is a carbon-oxygen single bond. Below that, it gets messy. This is what 800, 900 is where the fingerprint region is. It gets messy. Sometimes some strong bonds can be connected to carbon-halogen bonds, but it's very difficult because the fingerprint region, there is almost everything. So you can find something which, you can imagine something which is not there, or the other way around. You don't see something which is there because it's only overlapped with a lot of other peaks. So FTIR gives a lot of information, but on single functional groups. Now, add the version and an exam, you will see exercise like the one that I'm going to show you now. Let's do the strategy. Analyzing the spectra is like I was saying at the beginning, it's like solving a crime, solving a puzzle, whatever you want to say. You have a series of evidence, you cross-reference them, and at some point, you might need to go back and have a look, either confirming or discarding something when you go back and forth between the different spectra. And at some point, you need to make your mind up and say, according to all the evidence that they have, this is my molecule. Start analyzing this spectra quite systematically. So you start from degree of unsaturation. Fix this formula. There are a few formulas that I would like you to remember. This is one of them. There are other versions of the formula. For instance, I don't use, in my mind, when I try to calculate the degree of unsaturation, I don't use this one. But this is a very systematic one. If you do remember this formula, you can calculate all the degree of unsaturation that you want. Take note now because we're going to use it. Just remember, just looking at the formula, looking at the CHNOx. Oxygen never counts for the degree of unsaturation. Whatever oxygen doesn't count. It doesn't subtract protons or add protons. Instead, for instance, if you look to analyze the formula, A is the number of carbons, so minus B is the number of protons. Look at the other minus, E is the halogen. So each halogen is behaving from the saturation point of view, is behaving like a proton. Instead, the nitrogen, it looks like it's subtracting a proton. So when you have nitrogen, you treat the molecule like you could have a higher degree of unsaturation than you initially think. When you have halogens, normally it looks like, think about chlorobenzene compared to benzene. Exchanging one proton with a halogen doesn't change the degree of unsaturation. If instead you go for pyridine, you're diminishing the number of carbons, you're adding a nitrogen, and that changes compared to the initial formula you might think. But anyway, if you do remember this formula, it's very, very helpful because you need to calculate whatever formula you use, you should start with the calculation of the degree of unsaturation because that really helps. Then, normally the first spectrum I put is FTIR. We just discussed FTIR and familiar peaks. Look for amino groups. So you have, I will always give you formula. Always. There's going to be C, H, and whatever. You calculate your degree of unsaturation, but you also look at, for instance, there is nitrogen or there is oxygen. What do I see from nitrogen and oxygen on FTIR? Maybe you look for amino peaks. There is not amino peak, there is nitrogen, and maybe a nitro, but there must be some oxygen. And then you start connecting all the dots. Any familiar peaks on specific region around 3,000, if there is something, I expect aliphatic. 1,600-ish and high degree of unsaturation, that is telling you that there is an aromatic group. Mass spec. We discussed quite well the mass spec. That kind of fragmentation, loss of methyl, loss of water. You have an oxygen. Maybe you have an oxygen. Maybe you have a strong band, a very large broad band of 3,500. You imagine alcohol. You go to the mass spec and you look for, maybe there is the mass minus water, which is typical of the alcohol. Look for those. They can confirm or discard that that one is an alcohol. There are some recurrent numbers. Remember, the most recurrent ones are 43 and 91. 43 is the acetyl CH3 carbonyl. That is something that there is something which is isoelectronic with that, but is very rare. If you have 43, normally is CH3CO of the acetyl group. If you have 59, probably you have an ethyl and the ketone because it behaves the same way. But the ethyl itself can start fragmenting. Instead, 43 normally is a quite tall peak. The other tall peak that you want to remember from the mass spec is 91, which is the benzyl. All the rest can come from the calculation according to the structure that you start working out from all the rest of the spectra. So sometimes happens that you look at the mass spec, any immediate familiar peaks, yes, there are. You put something like, I see the 43 and I put it on one side. I know that that molecule has an acetyl group somewhere. We don't know where yet, but it has an acetyl group somewhere. You know that you have to place an acetyl. All the rest might come from deducting from all the rest of the spectra. They say you see on the proton NMR, you have an ethyl group. You might want to look at the mass spec and minus an ethyl group. Do I have this number? Yes, maybe it's a confirmation that you have an ethyl group or a methyl group, minus 15. Who knows? UV, again, if it's there, normally it's aromatic groups or very hyperconjugated groups. Most likely, it's very unlikely I'm not going to give you something which contains aromatics. It's very, very unlikely. That's why telling me that UV tells you something, it gives you 1 mark. Just don't forget to put it. Yes?
If you show the UV and it's not strongly, but it's not absorbent,
yeah,
do we need to say it's not an aromatic?
Absolutely. Yes. So absolutely. It could be that this whole aliphatic. I show you the UV. We will see some examples. If you don't see anything by UV, there is nothing which is absorbing. So probably you don't have neither aromatics nor conjugated systems. Absolutely. Most of the information, the most important information is given by proton and carbon. We saw that quite thoroughly. These are the questions you want to answer when you tackle proton and carbon. Always start with the number of signals, both in proton and carbons. In proton, number of chemical environments. In carbon, really number of carbons. Chemical shift, so where is this peak? If you imagine that that peak comes from something aliphatic, but it goes a much higher frequency, maybe it's connected to something electro-withdrawing, an oxygen, a nitro group, anything which is actually subtracting electrons. On the proton especially, be very careful with integration, because in the initial formula, I will give you a number of protons. Normally, they match perfectly. So if I give you 15 protons up there in the original formula, you should find them all in the proton NMR. So be careful with the integration. Be careful that the integration of your proton NMR matches with the number of protons that I give you. Then you can start seeing the splitting pattern, especially in the proton, because there is no splitting pattern in the carbon 30. Splitting pattern. So I see that, for instance, we saw that. I see that there is a triplet with a quartet. They look conjugated. Probably got an ethyl group. I see that this one is a 1.5 ppm, and it's a singlet. It looks like a methyl group. Look for the integration. Does it integrate 3? Maybe it's a methyl group. Does it integrate 6 compared to the rest? Maybe there are 2 methyl groups, but they are equivalent. It happens. Okay, so these are general information that you want to tell me about. So normally, and now we'll see with an example. Normally, I expect from you that you give me a very short report, which is the part that I say all considered. So after you analyze bit by bit, FTIR, mass spec, UV, proton NMR, you should have a little paragraph at the example of the workshop saying all considered, considering that I say, for instance, this peak by IR, and it's confirmed by carbon 13. I have this pattern on proton, so I have these groups. This cannot be this cannot be that. I confirm that this can work out this way. This is the formula. You should tell me, convince me that eventually, with all your evidence, you have the right formula. Now, I'll give you a few examples. It's gonna be now, from now on, it's gonna be almost a workshop. Only it's not assessed.
I love these questions.
I hope so. So let's start from that formula of there. Let's start from calculating the degree of unsaturation. Then we'll go bit by bit, and then I'll show you more or less, because you can use more words, you can use less words. As long as you give me all the possible information, you can get a good. Sometimes people historically got good marks even when they didn't get the final formula right, because they show me that they actually analyzed. Maybe they missed something which created a misunderstanding. But if you analyze all the spectra, you show me that you master this kind of methods well enough, you can get very good marks. And for me, I'm not really interested in you getting good marks. I'm interested that you understand the methods. Okay. So I give you maybe 3 or 4 exercises. It's going to be in order of difficulty. So this one is a very easy one. Don't be scared, but this is a very easy one. You don't need to start from one spectrum necessarily. You can start from wherever you want. For instance, if you see immediately the proton NMR gives you a very great clue, start with the proton NMR. You don't need to start with an FTIR or mass spec. I'll give you a couple of minutes, and then someone tells me, start guessing what is this one? How many unsaturations? You got 6 unsaturations.
Oh, you made me think I was so done. I can't do this. Sorry. It's an awareness. I genuinely think I thought 8 was a 6.
It's an 8.
I
So
still
let-
look at it and I still see a 6. So clearly I just remember.
Okay, I promise you it's an 8.
You see it?
So how many unsaturations?
0.
So from 2 you pass from to something in between. Let's look for something in between. We got 1 unsaturation. Oh, so 7, and then we have 1 unsaturation. What do you think this unsaturation can be? what this unsaturation will be. Consider the formula, consider the number of atoms and the kind of atoms we have. We have one unsaturation, what can it be? Clearly, remember that one cycle is an unsaturation. But if you put a cycle, you cannot put any other unsaturations if you have only one. But look at IR, for instance. I look at mass spec. What does the IR and mass spec tell you immediately?
There's a double range on
Which is called?
the carbon. What's a carbon?
Carbonate. Call it the way that it's called a carbonate in the helps. How do you know it's carbonate?
741.
That's good. Can you tell me? Yeah, but can you have any further confirmation it's a carbonate?
The mass spec.
The mass spec, what do you have on the mass spec? The 43, which is an acetal. So not only is a carbonyl, he has a methyl group next to it. Okay, what else? What can you say for sure? Again, that's a carbonyl. Where can you see a carbonyl? Quite clearly. NMR, where? The carbon 13. So the carbon 13 NMR. You remember that more or less, if it's around here, which is just over 170, what kind of carbonyl peak is there on the NMR? It's one carbonyl, but over 165, normally they are carbonyl peaks. Lower frequencies tells you something. Remember?
How close it is.
If it's carbonyls are between 165 and 200,
Yeah.
but the ketone is somewhere, the ester and amides are somewhere else. Lower frequencies means less electrophilic carbonyl. No, the other way around. Ketones are normally at 200, around 200. So that carbonyl could be a carbonyl of an ester. You have two oxygen. So one carbon is connected to an oxygen with a double bond, which is a carbonyl. From here, you already have this an ester. From the mass spec, it tells you it's an acetyl. So I think the molecule started building. Maybe you have an ester. That acetyl also has another oxygen. If you think that this one is indeed an ester. UV tells you that it's not a very, very strong absorption. You don't see too much of, so it's not aromatic. Plus you know that it's not aromatic because the degree of unsaturation shows that it cannot be an aromatic. What can you look? So look at the FTIR now. You have an ester. Can this one match with an ester? It can, but remember that taking the position, the carbonyl of the ester can move a little broadly speaking on the FTIR. So you cannot say for sure it's an ester, but there is something else on IR that might suggest an ester. So remember that I put on the FTIR numbers where I would like you to comment on the peak. So we said about 3,000 aliphatic, 1,200 something.
Yeah.
Single bonds. So that's a further definitive confirmation that it's an ester. Even if you know that it's an ester from the economy of the time, even if you know that it's an ester, because you say that's from, for instance, from the carbonyl peak, which reminds you of an ester, you go back to FTIR and you confirm, say something like that peak at 1243 might be the carbon-oxygen bond, single bond of an ester. If it's there, you should comment on it. Otherwise, you risk to lose easy marks. So don't take prisoner. Say everything you see. Proton NMR. What can you see from proton NMR?
Well, three environment,
3 environments, very good. So I always mention the number of environments. Then
the integrals tell you it's like 2, 3, 3.
so from here, I guess,
Yeah.
2, 3, 3.
Yeah.
Then multiplicity.
So I'm kind of guessing based on the structural seed, really. But the peak motion, I'm guessing is a triplet.
A bit more shifted. Yeah, is important. Want to see from your perspective? Yeah, maybe it's not that clear. On the picture, it's gonna be clearer. It's not that clear.
That's what I should.
That's it. Let's confirm it. So this one is a quarter. This one is a triplet. These two are coupled. They look coupled. Even if you don't take the ruler, you say that this is exactly the G doesn't tell you exactly what G, but they look coupled. So what is normally a triplet plus a quartet? A triplet will integrate 3 and a quartet which integrates 2. Normally on proton NMR, it tells you immediately it's an ethyl group. So a CH3, CH2. Then you have a singlet which integrates 3. What is the singlet that integrates 3? You know from the pika 43, it should be an acetyl. So on the one side, you start putting in your paper on one side, you know that I have this one because of the pika 43. You know that it might be connected to an oxygen because this carbonyl, it's an ester. What you need to put is then, this one looks like a quartet which integrates 2 protons. And this one is a triplet which integrates 3 protons. This one is a singlet which integrates 3 protons. This one most likely is this one. What are you missing? Probably something like that. What you're going to do now, what we didn't discuss yet, which can be used to start analyzing it or just saving the right confirmation. Remember, you need to tell me something about all the different spectrum. What can you tell me from the carbon-13? Let's say that you already think the proton NMR, and probably here from proton NMR and mass spec, you already know that this is the structure. So this is the structure. How can I confirm this structure by carbon-13? Because you would like to do it anyway. So you need to tell me that this one is confirmed by carbon-13.
The middle one.
So the top one is the depth. And I'm telling you the CH2 are down. This is the depth 135. What do we know from the depth? 1 CH2. So you know that you have one, you must have 1 methylene. What can I tell you? What about this thing? Either 2 CH3s, or it could be, if you don't know that this is the structure, it could be 1 CH, 1 CH3, or 2 CHs. 2 CH3 in this case might work. Yeah, 1 CH3 here, 1 CH3 there. It might work. Then you see what? A quaternary, which is the carbonyl. You know that you from the depth on the carbonyl, and all the quaternary disappear on the depth. If there were other peaks here and they disappear over there, they are also quaternary. So from the when you analyze carbon-13, what you should tell me is, I can see you analyze first the normal carbon-13. I can see 1, 2, 3, 4 carbons. I have 4 carbons over there, so the molecule is not symmetrical at all. I can see all carbons which are in the foreground. I count the number of carbons, then I count them. I can see 3 aliphatics, of which one is a methylene group. I know this is a methylene group because of it's upside down. The last thing I need to know is the carbonyl, which looks like a carbonyl from an ester because it's around 170. That is your structure. So that was the easy one. So first you start calculating the unsaturation. This is more or less what you want to report from the FTIR. Don't worry, I will give you all the slides if you need to practice. So there's no need to read them all. Mass spec, I got the 43. We didn't check the mass spec apart from the position 43. So let's go back. What do you see? I can tell you that M plus is 88. Try to do the calculation and see if the M plus is actually the whole weight of your molecule. So that M plus is the molecular ion. You can say it's very small, but it's there. So the structure is kind of stable, but not too much. It can fragment. What is the 29? The 29 is the ethyl group. So where does it come from? Fragmentation of this one. Although you already solved the puzzle, go back and be sure that you analyze all the potential peaks that I'm highlighting on the mass spec. Be sure that you do it. Don't discard anything. Oh. The most evident thing is 43 and 29. UV tells you that there is probably not aromatic. There is not a strong absorption. There is no aromatics. Carbon 13, 1 methylene, and 2, it could be CH or CH3. But apart from the carbonyl, there are no any other quaternary carbons. Proton and NMR, immediately, quartet and triplet coupled, typical of the ethyl group. The isolated peak of 2 ppm could be initially, if you're not sure, you can say that it could be the methyl group, because in here you need to tell me also all the integration. 8 protons, 3 different environments, 2 plus 3 plus 3. Then you should add this small paragraph, all considered. And when you say the all considered, you put all the information that leads you to your prediction. Okay, so in this case, it was very easy. I have a carbonite. I see from 3 different spectra. It looks like it's related to another oxygen because you know it's an ester. There are no other situations which are allowed. We have one unsaturation. That unsaturation must be the carbonite, because the carbonite is an unsaturation. Okay. This part of the ester, this part seems coming from an ester, which is confirmed by IR, and the 43 peak. So the whole molecule is simply ethyl acetate. You write this one, and if you give me all this kind of information, you get full marks. Now, let's go for this one instead. Let's start from. Let's take as much information as you can. Always starting from a degree of unsaturation. Again? Yes, because it's three double bonds plus one cycle, so it's always four population. Remember that each cycle, whatever the cycle is one of saturation. So, you have your structure already? Bless you.
Sorry.
Do you have the structure? Anyone? Okay, that's great. That's some of the structure. That's another very easy one. Okay. Everything, I mean, it needs to be increasing amount of difficulty. So how many saturations? 5 unsaturation sounds good. What can we know for sure? So 5 unsaturation, you look at the UV, there is it's quite a strong absorption. You imagine it might be an aromatic. But again, don't trust the UV. The UV should be another confirmation. How do you know that it's definitely aromatic? Mass spec because of
91.
the 91, excellent. And
The hydrogen,
proton.
the proton NMR.
Yes.
It's so shifted. That's in the aromatic.
That's aromatic. So you know you have an aromatic. That counts for 4 unsaturation. What is the 5th unsaturation? The carbonyl. So what can you tell me? What else can you tell me from? Well, anything. You tell me where to start from. Oh, you have that 43. We have the 91. Two in the same formula. 2 of the most recurrent magic numbers. Whenever you have something which is sure, put it on one side and say, I know you circle and say, I know this one is there. I just need to connect to something else. So we have 5 unsaturations. We have one aromatic ring. We have a carbonyl. We know from ion. What can I tell you from NMR? Proton NMR. From yes, of course. So if you have to analyze, start analyzing the proton NMR in the systematic way. Where do you start from? How many signals you see? 3 signals. How many protons you need to place? You have 10 protons. Can you find all the? Can you find a splitting of all 10 protons here? So if you know you have 10, look at the shape of the aromatic peak. Remember we discussed yesterday, how do I treat potentially substituted? Clearly this one is a substituted aromatic ring, but how substituted? You need to place, remember these integrals here are proportional. You need to place 10 protons. Can you find a way also using the mass spec that tells you the integration? What is the integration of this proton NMR? 10 protons. They have to come all together. So if you have 10 protons, you have this one, which means H3CO. You find it on the proton NMR. So you need to find something which integrates 3 H's. Plus on this one you have so you know that probably this one integrates 2 H. What is left? Considering 3 and 2, if this one comes indeed from 3 and 2, you have 10 minus 5, you miss 5 protons. You find them all on the proton NMR. Find all the protons. Give me the integration. Or you can start from here. It depends. Or you can start from the center. I don't know. Up to you.
I'd go,
You start from wherever you want.
yeah.
Sorry.
2.5,
Which one is 3?
the one that divides.
Okay. 3, 2, 5.
That was what my answer was.
Oh, if you have 5, what is it telling you? That this benzene probably is not further substituted. It's a multiplet. If it counts for 5, there is a huge chance that that benzene is monosubstituted. And the only substitution is the one of the benzyl, because you know from the 91. What about carbon 13?
One CH.
1 CH2. Then this one might be a CH or CH3. Those are aromatics. What can you tell me from the depth, apart from this position?
That the CH3 is
Yeah, look in this region. What disappear on the depth?
It's even.
Which is this one? There is another peak that disappears.
Okay.
Can you see this one?
Yeah.
It's not there. That's another quaternary. So I think we have all the pieces of information. We have this molecule. You have one methylene group on the depth. Yes, I do here. We have one quaternary, which is this one. Aromatic quaternary. All the rest is CHs, which are those. They go up. Even if they're aromatics, if they are CHs, they go up. If they're quaternary, disappear. So this one is CH aromatics. This one is a CH2. This one is a CH3. That's a carbonyl. So the molecule should be doesn't matter.
Yeah.
Are you sure? All consider we are happy that this is the molecule.
Yes.
FTIR, a little bit of aliphatics, not too tall because most of it was aromatics. Then definitely the carbonyl. Mass spec 43 and 91, very evident, typical recurrent numbers, magic numbers. UV, most likely aromatic. Methylenes, quaternary group that disappear on the depth, and you see all the rest of the aliphatic carbons. The system counts for 10 protons, so you need to find the 10 protons. A multiplet on the aromatic suggests monosubstituted benzene. The other two simplets, it means that you have two aliphatics which are not coupled with each other, and they are not coupled with anything else. If you have a singlet, it's not coupled, it's isolated. One integrates 2, one integrates 3. So, all considered, this is the molecule.
Yeah.
Okay? See, it's not difficult, it's fun. Now, let's make it a little more complicated. So I'm starting using most of the information that I normally use for exam questions. Remember the expansions. When I zoom on something, it means probably you want to have a look at the zoom. Look also at this one.
No, I'm trying to say. Maybe you have to say that.
I'm sorry, how was it when I was
I got 8. I think you don't get 8.
It got 8. Well,
Maybe.
who has got 8 or less or more? 8, we agree with 8?
You explain how you got that. 8 plus 2 is 30. 30 minus 15 is 15. 15 plus 1 is 16. 16 is 1 is 15. I don't say oh, something.
No, I did plus 5, so plus 1 with a 9, you know, don't know why. But this is.
Let's stick with the formula.
I just failed to learn. I think Einstein said that or something.
Yeah, I did say along with all
Yeah, you're 60.
Oh, it's saturated. It's well. But it's a lot of unsaturations, it's a lot of carbons, but can you see a lot of carbon? And look at the carbon, look at the proton and carbon 13. Proton and NMR and carbon 13 and NMR normally is the one that gives you probably the best, the most important information. Okay, what then we can find out. Look at IR. Right away. There is aromatics, yes. Notice I'm not even giving you the EV here.
Because it be so.
It will be so evident that sometimes you need composition. This is what you're doing in the lab. Sometimes, okay, why do I have to do UV if I don't really put aromatics? I know it's aromatic. Sometimes you don't do it. That would be good, nobody's stopping you. But sometimes it's redundant.
It's the screen between 10 and then
Okay. Is NH in general or NH as a monosubstitute? I will probably go for the mono. Yes, it's good. It's an amino peak, probably monosubstituted. Well, actually, not two substitutes. Monosubstituted, I mean, with one H only.
yeah, that's what
With one proton
One
only.
proton.
That's what I meant.
Yeah.
Then what do you have? What you cannot see by IR? But are peaks.
You cannot see any.
You cannot see carbon, of course, you don't have oxygen. You cannot see much else that is really important. You can see really, you can clearly see the aromatic, you can clearly see the aliphatic, you can clearly see the amino, that's it. Carbon 13, number of carbons. Remember, proton and NMR and carbon and NMR, you start from number of carbons and number of proton environments. How many? Let's start with carbon 13, for instance. What do you see?
Your aromatic.
Confirmation that it's aromatic. How many carbons? Let's start with the number of carbons. Remember this function is 1, 2, 3, and 4, 5. Consider that we have 14 carbons. What does it tell you? What suggests? Lots of symmetry. That helps a lot. What about the mass spec?
The 91 tells me.
91 tells you the benzyl. The benzyl is one aromatic, four unsaturated.
We've got 8.
You got 8.
Two unsaturation, benzyls.
Why not? Remember that the easiest answer normally is the correct one, or might be the correct one, but you need confirmation. What about proton and MR?
Big.
Big integration, quantify big. No, you don't. You have 15 protons. You have 15 protons to place.
10 on 7. No. On 7. Yes. No, it won't be 10.
8.
Because that's. Because we've only.
Remember, you need to place 15 protons.
Also, my perception is very bad.
But yeah, we can go 10 for 1.
Let's go for this one.
1. It's D2.
Go for more. 1, 2. Go for 3. Can I get any 3? No.
I got
Go for it. Go for it. Anyone for? No. This is 1. So.
Yeah, 1 for 10.
So we still need to place 14.
4 10.
14.
10. 4.
What did you say about the two benzyls? Does it match?
Yeah.
Plus? Where do they come from? Yeah, Charlie. That's right, correct. But where do they come from? The benzyl has 2, 5 on one side, the aromatics, plus 2.
5 plus 5 plus 2 is 12.
So we have 2 benzyls. 5 plus 5 plus the 2 methyls. What you're missing? Are you missing 1?
The nitrogen with the hydrogen.
Yes. So 1 proton.
Yes, you get credit for that.
What did I tell you that this stuff is going to be fun? You see? What did I tell you that this is fun? Oh. Degree of unsaturation, correct, 8. What do you see from FTIR? 3,000. 3,000, that one after 3,300 or less is a non-primary. So I've substituted with basically 1 NH. So you just connect the 2.
I knew I had. But when we got to the 2 benzyls.
Remember the symmetry. We were discussing the symmetry. You have the 2 benzyl rings, one on one side, you imagine the other one on the other side. What is missing? The NH. Just put it in the middle, you have your symmetry. Benzylamine. Remember all the consideration. I would like you to write even a little more than this one. This one will be the bare minimum. But try to write this one on the exam is a 25 mark question. Because the exam, the format of the exam is exactly the same as the second year exam. We'll have 7 questions, short questions, 6 for 7 and 1 for 8 marks. And then you'll have 3 25 marks questions, of which we need to choose 2. Yeah. So this one is always, I always put, there is not a chance I will not put this one.
And this wouldn't be like,
this one, the whole thing is going to be 25 marks. Then you need to choose one or the other 2, which is more likely is going to be retrosynthesis at one point. I'm sorry. Try to get this one good. You get a lot of points. But please do the retrosynthesis as well, because most of it is retrosynthesis. Okay. Yes. I'll give you this one as the last one for today, and then I'll see you at the workshop on Friday for this one, for this kind of exercise, okay? The one that you will do on Friday at the workshop, the report that you're gonna do is gonna be 25 marks. I mean, overall, it's like a 25 marks question at the exam. Please tackle it like it was an exam. Yes. Yes. I know. I spoke to Joel about that and say actually I don't like having them, but they're short assessments. So because of because since there are two short assessed ones, we decided to keep it in this way because of schedule. This one is more difficult, guys. Don't shoot the messenger. I'm the messenger.
It's definitely true. I managed to correct it this time. But when I'm down,
Shush! You're right. Let's just carry on, please.
Look how calm. Here, I'm even telling you exact integration.
Yeah, that's really nice.
Yes, but it's not gonna happen with workshops and exams. So
Can you make it clear enough? Because
it will be, I promise you, it will be clear enough. All the exercises, I test them, and I know for sure that there are no trick questions.
okay, that's where I get worried.
So let's do this one and then I'll leave you. But please practice a lot of the stuff. Don't remember now. I'll find out what the book with these kind of exercises, which is the final. You do this one. I'll check.
There's only three, there's three.
I don't know if they're on. Are you sure?
Q-U-A-R-T E-R-N-A-R. Water is Q-U-A-R-T-E-R. Nary is N-A-R.
I feel like there's not an R in water.
There is.
Yeah. No, it's in the middle.
No, it's not.
or is it quantum?
It's Q-U-A-R.
Make you flash it.
Well, it's a good thing we're not master. There's two options. But
It's
not
not
one.
not in a big water.
There is. Oh. Yeah. Oh, there's no. T. You know, Q-U-A-R-T. That R's there. Anyway, it's clear language whilst we go and tell that.
The book you want to look at is organic structure for spectra, and the first author is field. So look at the field I take my exercise from there. Field. Around 250 questions.
That's how you spell question. Yeah, we discussed that. We've got it. But.
Field is the name of the main, if you look for organic structure from spectra, stuff like that, or field, this is the book you want.
What books do I want? I love that.
Yeah. Field. There are something like maybe a little short at 300 exercises. One of them is going to be at your exam. Buy that book. If you do that, if you practice, I'm sure you don't need the book. You don't need to remember. By the time you solve all the exercises, so if you ever look at all the exercises, I promise you, swear, 100%.
Can you read all this try and learn?
If you learn how to do everyone, you don't need a book. I promise you. And the exercise is normally not super complicated, not as easy as this one. So it could be a little more complicated than those, not too much.
Is it just a with fashion then?
No, there is some theory before.
Yeah.
There is some good explanation on why, because this is what you want to do. And then at the end, there are a lot of exercises. One, I promise you, one of these exercises is the one you find out exam.
I'm not saying we
I gave you enough information already, maybe too much. I'm sure that if you do all the book, considering that it's a closed book exam, if you can do the whole book, I'm absolutely 100% sure that you get all the marks. Unless you tell me the structure and you don't report anything about that. In that case, even if structure is the whole structure correct, I'm not gonna tell you exactly the marking scheme, but even the whole structure is correct. With not much explanation, it is about 5 minutes. 4 marks, 5 minutes.
And then you that 14.
which one?
Starting from where or which?
The 2A. On the roast man.
Yeah.
How many splitting is that?
A lot. But it looks like a triplet. Looking at it from close, I can tell you that it looks like a triplet of double. Okay. Tell me something, guys. Where do we start from? We don't have any of the magic picks on this one, which happens on the mass spec. Any of the magic numbers, recurrent ones. How many unsaturations we said? We all agree with 2 unsaturations, okay? What are the unsaturations? Well, we cannot say for sure, but what we know for sure is that there is a nitrogen.
There's a C double bond to the nitrogen. Based on the 2.
A C double bonds to the nitrogen. We'll see.
Based on the 2114.
Well, triple one.
Sure.
Theoretically good.
See in there, where I see the triple. I'm not saying it can't, you're just saying most of them.
But that's in the double bond region.
Is it?
2000.
Triple.
What's, oh yeah, it's 17 for a double bond.
Who said triple bonds? We'll find out. We'll see. Could be a triple bond. Where is the triple bond? What is the triple bond connected to? Could be. It could be. So you use the other spectra to confirm or discard it.
Yeah.
Well, this is why you count the number of unsaturations, the number of hydrogen missing if you were saturated. So that's a good consideration. Yes.
There,
Okay.
yeah. Sorry.
Let's go. Let's go for carbon 13. What can you say from carbon 13 NMR? 5 different carbons. Indeed.
The oxygen that makes the free bonding oxygen.
It can if it's protonated, but no. What's the problem?
Triple one down. He was like, triple one down. And I was like, and oxygen doesn't make very much.
So today we started with a proper one. Actually. So I don't know if you were there, but there was we waited for the fire brigade to arrive. Okay, it's a drill. It's a drill. It's a drill. It's not a drill. No, it's not a drill. So apparently it was a dodgy sensor that went on, but until you check. Anyway. I don't think so. Maybe it's for recording, but I don't know. Maybe
Definitely have to.
I don't know. So let's go back. I love if someone start watching the recording of this one. There's so much chatting and rubbish going on. Oh, is there a fire alarm? Oh, is there a camera? Oh, okay. So what? So we stuck at carbon 13, and carbon 13 tells me 5 different environments, so no symmetry because we have 5 carbons over there. What tells you also? 3 CH2 groups and one on top of one other CH or CH3, who knows? This one quaternary because it disappears from the depth. So this is what we know. So we need to place 3 CH2s. We see 3 CH2s here. We also see on the proton something which exchanges with the 2O. What do we connect it to? We have nitrogen. We have amino groups. It could be an NH2. Because I'm telling you, it breaks 2. It could be an NH2. If you are at the exam, you put it on one side. You say, okay, look at that. Exchanges with the 2. Sounds fishy. Has to be, if it's an amino, sounds fishy is the right word. Because they smell fishy. The NMR, if you do it in the right condition, will tell you, because if you, let's say that this one was in fluorophore, you have that peak, you put a couple of drops of deuterated water, that peak disappears, that one exchanges with D2O. When I say exchanges with D2O, it means that if I put D2O, this one will disappear, exchange, because you exchange the proton that you see here. If it exchanges with deuterium, it will disappear because you can see the deuterium on the NMR. So when it exchanges with the code, this is what that means. So we have 3 probably coupled CH2s, 1 terminal NH. We have So the from the NH cannot come in saturation because NH2 means saturated. We have two saturations to place. We may have a triple bond. Any idea of the structure? Can the triple bond be? So a triple bond could be a nitrile. If a triple bond is a nitrile, it's C triple bond N, but then you'll miss the nitrogen connected with 2H, which is most likely coming from here. So maybe it's an alkyne. Maybe it's a triple bond of carbon-carbon. Okay. So from the here, this is what we see. It looks like a primary amino peak, especially because that shape of the amino group on the IR reminds you of a primary, so NH2, which you can immediately confirm with this one. It might be the confirmation because there are two protons which exchange with the two in one single environment. So it's one singlet which integrates two and exchanges with the two.
Yeah.
Mass spec, you don't see much. You see, this is one of the times where you cannot see much on mass spec, but the mass is 83 and the tall peak is 82. So there is a difference of 1. Remember what we said about the difference of 1 in the mass spec. Normally comes either from an aldehyde or it comes from a terminal alkyne. So a C triple bond C with the H terminal. The only thing that actually gives you a difference of 1 is actually the aldehyde or this one. All the rest is very likely that you just take one proton from it. But those protons are more mobile in the mass spec. From the mass spec, you cannot see too much apart from that. And the peaks are 55. It will come after you guess the structure. Then you go back and say, okay, this is why. So sometimes not necessarily you can identify immediately the peaks on the mass spec. Sometimes you do it retrospectively. You try to guess the structure and you for confirmation on the mass spec. This is one of the cases. Carbon-13, as usual, tells you a lot. 3 different methylene groups, 3 different ones. We saw that there is no symmetry at all. Proton NMR, the sister comes from 9 protons, but the system comes from 9 protons, but we have many signals. Most of them are from the CH2, apart from the one who was on the far right, which exchanges with the 2, which might be connected to the amino group. Okay? So this is the structure you want to see. The mass spec really tells you something. The 82, 83 peaks, either it's an aldehyde or it's a terminal alkyne. Terminal alkyne is more likely because there is no carbonyl. If there is no carbonyl, it cannot have aldehyde. Okay? NH2 is, yeah?
Is 2.
Absolutely. One double bond is one saturation, the other double bond, the other pi bond is the second saturation. Yes.
A triple bond comes with 2
Remember, I have to take for granted that you know that that a triple bond comes. I have to take for granted that you know that a triple bond comes with 2 unsaturations.
I didn't go like, well, people in the group place, I thought I was wrong.
I didn't.
I thought it was 1.
I said it was a question.
Mm.
I was like,
When I said it, something different.
Like when we do mechanism and we say something, let's be sure that whatever we're saying is plausible from a chemistry point of view. This one, which I leave you for home as a practice, this is complicated, okay? Not super complicated, but this is definitely the most complicated of the whole set today. You can do this one with confidence, you'll be fine at the exam, I promise.
What level of 1, 2, 3, 4 do you reckon 5. 1.
So let's say between It's easier when you know the answer. Let's put it this way. So it's a difficult question to answer. But let's say that normally is between the previous one and this one. So this one can be actually complicated. I don't know. Then you tell me, maybe you find it very easy.
No, that was really too hard.
But
Really, really, the first one.
It's really easy. Like, it's not harder, but.
With spelling carbon monoxide for some reason.